Okay, 1, 2, 3.
Good morning. Welcome to STEM Lockdown Digital School. I'm presenting physical science for grade 11. I'm Mosala Liburu. You can get me on Twitter at MosalaDL and also on Instagram. It is my handle there is post_silicon.
Mosala, your mic is muted. There you go.
Thank you. All right, thank you. Now, let me just start. We're busy with this exercise last time, so I want us to go through it together. So it reads, the opening sentence read, the decomposition of hydrogen peroxide in the presence of a catalyst at standard pressure and room temperature is given by the unbalanced equation, chemical equation below. And then oxygen is collected and the volume is recorded over a period of time. The reaction is complete at time t. So the results below are plotted on a graph of volume of oxygen versus time as shown in the diagram below. Right, now the first question was, first thing you have to take the molar volume of a gas as 24,45 cubic decimeter at room temperature and standard pressure. And then the first thing was to balance the equation, and then how would the catalyst affect the reaction, and then you were to use the information on the graph to calculate the mass of hydrogen peroxide that decomposed. So let's see, how do you balance the equation? Right. The first thing is that if you look at this equation, you can see that on the left-hand side, there are 2 oxygen atoms, and on the right-hand side, there are 3 oxygen atoms. So if we put a 2 here, we are having how many hydrogen? 4 on the right and 2 on the left. And then now, what we do, we then put a 2 here to have 4 on the left of hydrogen and also 4 on the left of on the right of hydrogen. Let's look at oxygen atoms. It is 2 times 2 on the right, on the left, and then on the right it is 2 plus 2, which is 4. So it means the equation is balanced. So the yellow equation is the balanced equation, as the question was asking. And then you are asked, what is the role of the catalyst? So the role of the catalyst will be to increase the rate of the reaction or to make the reaction faster. But more importantly, it makes the reaction to be faster by lowering the activation energy. It makes the activation energy lower. You will see in the next coming lesson, we'll be talking a lot about activation energy. Right. The next question was to determine the volume of hydrogen peroxide that would have decomposed. So in there, what is that we know? We know that, let's look at how we go about it on option 1. We know that number of moles equals to volume over molar volume. So now, in here, we are going to say, let's go back to our graph and see If you look at the volume there, when the reaction is complete at time t, it's 600 cubic centimeters. Now, remember, we are dealing with concentration in and volume in standard units, which is decimeter cubic. So in here, we have to convert this cubic centimeters into decimeter cubic. So by doing that, we are going to be dividing this 600 by 1,000. So that is why we are having number of moles equals to what? V, which is the volume, and then the volume it will, instead of being 600, it will be 600 divided by 1,000, which is 0.6, and then we're given the molar volume at that temperature was 24.45. So there we substitute it. Then we get the number of moles of oxygens that were produced under that condition. Now we look at the equation. Let's go back to the equation. If we look at this equation, 2 moles of hydrogen peroxide will produce 1 mole of oxygen. So it means this number of moles have to be multiplied by 2 because they are of oxygen, is the number of moles produced of oxygen. Then to get the number of moles of hydrogen peroxide, you have to multiply whatever number you are having of oxygen by 2, because you can see that they are in a ratio of 2:1. Hydrogen peroxide, 2 moles produce 1 mole of oxygen. So you have to multiply the number of moles of oxygen by 2. Then you multiply this 0.245 by 2, you get 0.049. So that's the number of moles that will be getting, that would have reacted of hydrogen peroxide. But you have been asked the mass. So what will be the mass? So we know that the mass is equals, the number of moles equals to mass over molar mass. So number of moles will be mass over molar mass. So what will be happening there is that you are having mass which is unknown, and then the number of moles is 0.049, and then what is a molar mass of hydrogen peroxide? It will be 2 hydrogens, each one of them will be 1, so it will be 2 times 1 plus 2 times 16, which is 32, so it will be 34. So you will be dividing by 34, and then if you cross multiply, you will be getting your mass to be 1.67. Right. Let's look at option 2. Option 2 is to say 68 grams, because you know that you'll be having two of this. You are having 2 moles of hydrogen peroxide, so it will be 34 times 2, so 68 grams will be producing 24.45 volume of oxygen. Now we want to know how many grams will be producing 600 cubic decimeter times 10 to the power minus 3 decimeter. Remember, this is the same as 0.6, because it's like you are having 600 multiplied by 10 to the minus 3 is the same as divide by 1,000, because you need to convert that to decimeter cubic. Right, so if you want to know how many grams will produce this volume, so you just say X here. Then after that, you cross multiply. You know that 68 gram will produce 24,45. And then you do not know how many grams will give you 0,6. That is 600 times 10 to the power minus 3, because this was 600 cubic centimeters. Then you are converting it to a cubic decimeter. So you have to multiply by 10 to the power 3. So how many grams will give you this? Then you cross multiply. Then we end up having x equals to 68 times 0,6. This is the 0,6 divided by 24,45. Then you'll be getting the same answer. So you look at a method that you find it to be comfortable with, and then work your answer out from there. If you find this method to be easier, you can go for it. You don't have to do two methods. You have to do one method, because you'll be allocated time to do just one method. Right. Let's look at the next question. It says, in the experiment, Elena adds 500 cubic centimeters of hydrochloric acid with concentration of 0,36 to 1.2 gram of magnesium in a test tube. She records the change in mass of magnesium as the reaction proceeds at regular interval. The balanced chemical equation for this reaction is given here, and then the change in mass of magnesium during the reaction is shown on the graph below. So this is the change in mass of magnesium over time. Now, identify the limiting reagent and give a reason for that. That's the first question. And then the second question is to calculate the number of moles of unreacted hydrochloric acid in the test tube. So already here you can see that the limiting reagent will be magnesium, because you are having also unreacted hydrochloric acid. But also, if we are looking at the graph, is that after 3 minutes, that is after 3 minutes or 3 units of time, magnesium was the mass of magnesium was 0. So it means magnesium was used up. So magnesium will be our limiting reagent. And then our hydrochloric acid will be the reagent that is in excess. So identify the limiting reagent in this reaction. It is magnesium. Why? Because after 3 minutes, magnesium was used up. There was no magnesium left. It was used up. All the magnesium was used up. And then we have to calculate the number of moles of unreacted hydrochloric acid in the test tube. Right. So we have said that the limiting reagent is magnesium, and then the reason for that is that after 3 minutes or at the end of the reaction, the mass of magnesium was 0, or magnesium was used up. Now let's try to get the number of the mass of hydrochloric acid that was in, calculate the number of moles of unreacted hydrochloric acid. So let's start here by saying, we start by firstly knowing, calculating the number of moles of magnesium that was there. So we can do that by saying concentration, we're given concentration of magnesium, which sort of hydrochloric acid, which is 0,36. And then the number of moles is what we do not know. And the volume there was 500 cubic centimeters. And what did we say about 500 cubic centimeter? It needs to be converted to decimeter, to cubic decimeter. So by if we convert that, we divide by 1,000 and we'll be getting this value to be 0.5. Right, let's continue. So we've got a number of moles of hydrochloric acid that was used there, and then now we want to know the number that the number of moles that did not react. So the second thing it is to look at the number of moles of what? Of magnesium that reacted. So what is that we know? We know that number of moles will be given by mass over molar mass. So in here, the mass of magnesium that was used was 1,2, and then we say it will be 1,2, and the molar mass of magnesium is 24. So the number of moles of magnesium will be 0,05 mole. That would have reacted. That was used actually. Now we look at our balance reaction equation. If we look back at our balance equation, you can see that 1 mole of magnesium react with 2 mole of hydrochloric acid. So let's go back here. So it means 1 magnesium is to 2 mole of hydrochloric acid. Now it means if magnesium was 0,05, it will be 0,05 multiplied by 2, which is 0,1 of magnesium that would have reacted. Now, the number of moles of magnesium that would have not reacted, the unreacted, will be the number of moles of hydrochloric acid that would have not reacted would be the number of moles of hydrochloric acid that was used minus the one that reacted. And then that will give you the unused. So then moles of magnesium left in the test tube, that is the one that did not react, the unreacted one, will be the number of moles that was used of hydrochloric acid minus the one that reacted. So it will be 0,08 mole. Right, let's try to do this. I'm not sure if there's any question there. Any question? All right. Okay, let's continue. Right, now let's do this exercise. The first question it is, you can take a snapshot of this question. What is a standard solution? That's the first question. And what is the molar mass of potassium dichromate? And then the other question is 30 grams of potassium dichromate is dissolved in 500 ml of water. What is the concentration in mole per cubic decimeter of the solution of potassium dichromate? And then how many grams of magnesium chloride crystal will be required to prepare a solution of 1 mole per cubic decimeter concentration in a 250 cubic centimeter volumetric flask? Right. The other thing that I need to make you aware is that concentration, if it's volume, if it's given in milliliters, you still divide by 1,000 to convert to cubic decimeters. And then even if it's given in cubic centimeters, you divide by 1,000 to convert to cubic decimeters. So let's continue and try to answer these questions together. Now, this is based on our activity that we did on our previous classes. What is a standard solution? A standard solution, Okay, a standard solution is the solution whose exact concentration is known. And then the next question was to determine the molar mass of potassium dichromate. So to determine the molar mass of potassium dichromate, it is to say potassium is, there are 2 potassium atoms here, so it's 2 times 39 plus chromium, there are 2 of those, is 2 times 52. Oxygen, there are 7 of those, so it's 7 times 16. So if you add them together, you'll be getting 294 grams per mole. That is the molar mass of potassium dichromate. Then let's continue. You were asked to determine the mass that will be required to prepare 1 mole. Let's go back to the question. How many grams of magnesium chloride crystals will be required to prepare a solution of 1 mole per cubic decimeter concentration in a 250 cubic centimeter volumetric flask? So we want to know, we know that we are required to prepare a solution of this concentration in this container, but we want to know how many grams of magnesium chloride. So in here, we would know that concentration is equal to number of moles over volume. Now, we would say we are preparing a solution of 1 mole per cubic decimeter. So the concentration is 1 equals to number of moles is what we do not know because we don't even know the mass that is required. So the volume here, it was in a 250 cubic centimeter. So we divide that by 1,000, we get 0.25, right? So the number of moles it will be, when you cross multiply, you'll be getting the number of moles is 0.25 mole. That will be required. Now we know the number of moles. So we know that number of moles equals to mass over molar mass. So mass over molar mass will give us the number of moles. So we know the number of moles, we have calculated it to be 0.25. Then the mass is what is unknown. Then the molar mass, this is how we calculated it. We said is magnesium 24 plus 2 chlorine atoms is 2 times 35,5, which is 71 plus 24, which is 95. So that is the number of moles of that is the molar mass of magnesium chloride. Now, what will be ultimately what will be the mass that will be required? Ultimately, the mass of magnesium chloride that will be required will be 23.75 grams. That the mass that you need to weigh and transfer it into a 250 cubic centimeter volumetric flask and fill it with water to make a solution of a concentration of 1 mole per cubic decimeter. Right. Let's you can, have a snapshot of this, but you can always view this later on YouTube. But consider the following reaction. Right, if you are having iron oxide, ferric oxide, plus carbon monoxide, giving you iron plus carbon dioxide. This is the reaction that is used, that normally take place when we are refining iron. So the first question was balance the above equation, and the second question was calculate the mass of iron in tons produced from 50 times 10 to the power 3 kg of ferrous oxide or iron 3 oxide. Right. So the third question was that a sample of iron ore contains 15% of ferric oxide or iron 3 oxide. So how many kilograms of iron will be produced from this ore sample if the mass of the ore is 1 ton? So 1 ton, remember, it's equals to what? 1,000 kilograms. So let's start off by trying to balance this equation. Trying to balance this equation will go like this. You are having iron oxide plus 3 carbon monoxide, giving you 2 iron atoms plus 3 carbon dioxide molecules. So this is what will be happening here. You just put a 3 in front of a carbon, then oxygens. Let's just see the iron atoms. There are 2 on the left, 2 on the right. Oxygen is how many? Is 3 plus 3, which is 6, and then 3 times 2, 3 times 2, which will be 6 also on the right. So the carbons is 3 on the left, 3 on the right. So the equation is balanced. Now, the second question that we were asked there was to calculate the mass of iron in tons that will be produced from 50 times 10 to the power 3 kilogram of iron oxide, iron 3 oxide. So in there, this is how you're going to be doing it. You say we want to know the mass, but we cannot directly go on and get the mass. So what we need to know is that from this balance equation, we can see that we just want to know the number of moles of iron oxide that were there. So in here, we say number of moles is mass over molar mass. So in doing that, we can substitute the mass that was given there is 10 of iron oxide is 50 times 10 to the power 3. And then what is the molar mass of iron oxide? It is 2 times iron, which is 2 times 56 plus 3 times 16, which is 160. So it will give you what? It will give you 312.5 times 10 to the power 3, or 3,125 times 10 to the power 5 mole. So that is, if you write it in scientific notation, it will be 3,125 times 10 to the power 5 mole. So now we know that 1 mole of iron oxide produces 2 moles of iron. 1 mole of iron oxide produces 2 moles of iron atoms. So now it means 1 mole produces 2 of this. Now we can say that therefore the number of moles of iron atoms will be of iron will be 2 times this, which is 6,25 times 10 to the power 5 mole. So we want to know what will be the mass of iron that will be produced. So we know the number of moles equals to mass over molar mass. So the number of moles of iron, we have said, is 6,25 times 10 to the power 5. So we substitute it here. And then the mass is what we are looking for. And then molar mass of iron is 56. So this is 56 times this, which is 3,5 times 10 to the power 7 gram. Remember, this is in gram, and then in kilogram it will be 35,000 kilogram. So this is, we have to determine this in tons. So 1,000 kilogram is equals to 1 ton. So it means this will be 35 tons of iron that will be produced. Right. the last question was that a sample of iron ore contains 15% of iron oxide. How many kilograms of iron will be produced from this ore sample if its mass is 1 ton? Right, let's continue. Now, 15% of this is equals to iron oxide. So 1 ton is 1,000. So it's 15%, 15 over 100 multiplied by 1,000, which is 1 ton equals to 1,000 kilogram. So this will give us 150 kilogram of iron oxide. So from this 150 kilogram of iron oxide, we want to know how much of iron will be produced. So we start by determining the number of moles of iron oxide that will be produced there. So we say number of moles equals to mass over molar mass. So in here we know that this is equals to what? Equals to 160. So okay, let's see here. I think there was an error here. Let's just deal with it. So that will then be 150, and then because this is kg, you have to say 1,000. Sorry, so 1,000. So this will be 0.9375 multiplied by 1,000, which will give you 9. This should be giving you 937,5 mole. So this will give you 937,5 mole. And then that will be the number of moles of, remember this is not 150, it is 150 kg, which is 150,000, because here we are working in grams. Now, 1 mole of this will give you 2 grams of this. So it will be the number of moles of iron will then be 1,875 times 10 to the power 3. Because of this kg, always you are multiplying by 1,000. Then the mass, the number of moles will be 1,87 times 10 to the power 3. Multiply by this 56, it should be the mass should be of iron will be 105 times 10 to the power 3. 105 times 10 to the power minus 3. That will be the mass of iron that will be produced in kilograms. Right. The next question was what is an empirical formula? What is an empirical formula, and determine the molar mass, the molar formula, the molecular formula of a compound with a molar mass of 88 grams per mole, and having this composition 53.55% of carbon and 9.09 of hydrogen and 36.36 of oxygen. So now we want to, the first question is, what is an empirical formula? So an empirical formula is the simplest ratio in which elements combine in a compound. An empirical formula, it is a simplest ratio in which elements combine in a compound. Right, so that's the empirical formula. Then we are asked to determine the molecular formula of what? The molecular formula of a compound with this molar mass of 88 gram per mole and 53.55% of carbon and 9.09 of hydrogen and 36.36% of oxygen. Right, in here, what we do, we want to determine the molecular formula of this compound. So we know that the carbon content of this particular element is 53.55. So, and then the hydrogen composition in terms of per 100 is 9.09, and the oxygen is 36.36. So we divide this by molar mass. So molar mass 53.55 divided by 12, which is the molar mass of carbon, will give you a 4.46, and then 9.09 divided by 1 will be 9.09, and then the oxygen here is 36.36 divided by 16, which will be 2.27. Then we divide every number with the smallest number and round it to the nearest whole number. Now, 2.27 divided by 2.27, it will be 1. 9.09 divided by 2.27, it will be a 4. And then 4.6 divided by 2.27, it will round off to be a 2. Now it means the empirical formula is C2H4 and oxygen. Right, so that's the empirical formula. But now we know that the molar mass of this empirical formula will then be 2 carbons, which is 2 times 12, plus 4 times 1, which will then be 4, plus 16. It will give you 44 grams per mole. Now, if you divide the molecular mass by this molecular mass of an empirical formula, you'll be getting a 2. So it means you have to multiply the empirical formula by 2 to get the molecular formula. Right. So in the next few minutes, I will be projecting the exercises that you will need to do at home. So this will be the exercises. You can have a snapshot for now and or look at them later on YouTube. But this is the first exercise. You've got the next 2 minutes to copy it down. All right, let's go to the next exercise that you need to copy and do it at home. So I hope you have managed to take a snapshot of it. And this is the last one that you have to do. Okay, thank you, ladies and gentlemen, for your attention. So this is what will be happening tomorrow. We'll start with the solutions of this exercise. Please try these ones at home tonight and ensure that tomorrow you come prepared with the solution. We are going to be doing solutions together, and we'll also start something new which will be based on energy changes tomorrow. So until then, thanks for being good listeners. See you then. Bye-bye. So